Hello, we are Team Billee from Poly Pomona. This is our second year participating in the University Rover Challenge, and we're excited to show you what we've done this year. All of our rover's main subsystems from last year have been redesigned and rebuilt to tackle each mission with an improved or new approach.
This year, we reduced the size of our chassis due to better, more compact hardware packaging. This retains the modular and dust-resistant design while also lowering the center of gravity. Our rocker bogie suspension system has been redesigned with targeted optimizations in geometry and weight. We accomplished this through extensive structural analysis to remove unneeded material and add reinforcements where needed. The wheel positions and linkages have been fine-tuned for enhanced stability and improved traversal capabilities while modules are installed.
For our electrical systems, a key change from last year is the reduction in the number of batteries on the rover, helping to decrease both weight and overall runtime. To power our logic systems, we are utilizing a dual battery system with two different voltages. One powers the logic, while another powers the arm inside the phones. Another significant improvement is the streamlined use of external hardware. Previously, we had redundant components and connections that have now been eliminated. The arm is now fully integrated with its motor controllers and encoders, all directly attached for more efficient operation and weight reduction. Last year, we encountered challenges with communication range and connectivity. To address this, we've upgraded our ubiquity system with an overall higher gain and frequency.
Along with that, our team has begun creating custom PCBs for the first time to consolidate components into a more compact space, allowing for weight reduction and more room for other internal components. This PCB is used for wheel motor control, temperature and voltage monitoring, and receiving information from the controller.
The science module includes a go-direct spectrophysics plus spectrophotometer, positioned inside the rover to help detect possible signs of life in soil samples. It operates using absorption spectroscopy and Beer-Lambder's law. In our science plan, we will use data collected for a protein concentration analysis with the BioRad protein assay, where absorbance at 595 nanometers will help quantify protein levels. The absorbance measured would then be proportional to the concentration.
For our sample collection system, we opted for a custom-built core drill that slides along a linear rail. Once the drill reaches 10 centimeters below the surface, it lifts and deposits the soil sample into an awaiting cache. The cache is then sealed to preserve the sample's integrity until it can be collected for future analysis. To detect the presence of life on Mars, our team has decided to improve upon our ultraviolet spectroscopy system. Utilizing different wavelengths, different minerals can be detected, specifically calcite, which has ties to both microbial activity as well as evidence of water. For deployment, our team has developed a tension and bellow folding system that encases soils or rocks in complete darkness, allowing our 295 nanometer UV light to take full effect.
This year, we built an articulated 5-degree of freedom robotic arm with the all-new lightweight design using aluminum 6061 extrusions. On the first axis, we use a brushless DC motor with encoders coupled with a worm and spur gears to minimize backlash. This ensures smoother, more predictable movement for the arm. We also have a 100-to-1 planetary gearbox for the second axis to ensure that the base has enough torque to drive the entire arm. On the third axis, we want to focus on accuracy and precision. To do this, we use a harmonic reducer motor that eliminates backlash as well as an offset of the second axis to allow a full 270 degrees of rotation. For the fourth and fifth axes, we decided to keep the optimal design of the differential system that allows the end effector to move in its yaw and pitch axes. This year, the arm is being controlled by encoders and a TNZ 4.0, which sends signals via pulse width modulation to each motor. We also focus heavily on implementing the inverse kinematics in our approach to controls. By identifying the location and orientation of each motor, we assigned its frames following the Vanderbilt-Hardenberg representation. Then by using this information, we were able to generate a series of homogeneous linear transformation matrices to develop and solve for the forward and inverse kinematics.
This year, we used ROS2 for our control stack. We've migrated a significant portion of our workflow to Docker containers, including a Docker container deployed on our Jetson or Nano, to streamline workflow and resolve dependency issues. We integrated more complex and sophisticated libraries such as MoveIt for arm motion planning and Nav for autonomous routines. We are using the Intel RealSense depth camera and have developed a custom vision pipeline, utilizing a web server to stream our camera feeds to a client laptop. In our vision stack, we were able to detect Arupa tags and have used the YOLO V5 model to track objects such as the water bottle for autonomous tasks.